Hello, Science 20s. Our lesson today is on oil refining. We are going to identify hydrocarbons as a source of fossil fuels, and we're going to look at two processes on breaking down these fossil fuels. To me, this is a very important topic because we live in Alberta and fossil fuels is one of our main industries. So, for oil refining, what we start with is we have crude oil and it is pumped from the ground through pump jacks throughout Alberta. And I'm sure driving down the highway, you've seen these pump jacks on the side of the road on farmers' fields. The crude oil, then, after it's been pumped out of the ground, is shipped through pipelines to different oil refineries. Now, much of this shipping actually occurs through Alberta to other provinces and to other countries. And so we can see here's our oil pipelines. Up here is Edmonton, and we can see there's a number of different pipelines that go not only across Canada, but also down into the United States.
In this video, you will learn how fractional distillation separates crude oil into useful fractions. Crude oil is the term used to describe unprocessed oil. That is oil that has been taken directly out of the ground, either on land or under the sea. It is an exceptionally valuable resource. It provides us with a great number of hydrocarbons, some of which are useful as fuels, and others are used in the manufacture of many different chemicals and even plastics. However, in the raw form as crude oil, it can be a viscous, dark-coloured tar-like consistency, and the different fractions of hydrocarbons must be separated by fractional distillation for them to be useful. Before we understand how fractional distillation works, we should be clear that crude oil is a mixture of hydrocarbons with different chain lengths, some being short molecules and some being very long. Intermolecular forces act between molecules, and the longer the molecule, the greater the intermolecular force. As you can see here, the small molecules have weaker intermolecular forces, and so will require less energy to break them apart and turn them into a gas. They have a lower boiling point. The longer molecules have greater intermolecular forces. More energy is required. A higher temperature will be needed to evaporate these molecules. They have a higher boiling point. Now we understand how chain length is related to the boiling point of a molecule. Let us look at how this method works. As you can see, crude oil is heated up to a high temperature outside of the fractionating column. The hot crude oil, now mostly in vapor form, is pumped into the column. The column has a heat gradient and is very hot at the bottom, going cooler as we move up to the top. Even at the very bottom of the column, where the temperature is still high, some long chain molecules with high boiling points begin to condense back into a liquid. These are collected at the bottom of the column. The rest of the molecules start to rise up the column, making their way through bubble caps in each tray. The bubble caps slow down the rate of the rising vapor, and eventually the vapors get too cool, condense, and are collected as liquids in the trays. Small molecules have low boiling points, and so condense much higher in the column, where the temperature is cooler still. As you can see, hydrocarbons with similar boiling points are collected in the same tray, and this is why they are known as fractions. They are mixtures of hydrocarbons with similar boiling points. Each fraction has some important uses. Some examples of fractions are petrol, useful as a fuel for cars; naphtha, used in the manufacture of chemicals; kerosene as aircraft fuel; diesel oil, used as fuels for vans, cars and lorries; and bitumen, a mixture of large chain hydrocarbons used to lay roads. Now, at the end of this video, you should understand that crude oil is a mixture of important hydrocarbons, and that fractional distillation is the method used to separate crude oil into useful fractions with similar boiling point. You should understand that small chain molecules are collected at the top of the column since they have lower boiling points, and larger chain molecules are collected further down the column as these have higher boiling points.
Okay, so let's take a look at this fractional distillation. Again, fractional distillation is a physical process for separating something. So again, what they do is we're pumping in this raw crude oil and we're heating it up. And we're going to use the differences in boiling points to separate out small chain hydrocarbons at the top from very long, large chain hydrocarbons at the bottom. This is why also, if you look at the examples, at the top, we have the small molecules. These are the things that are 1, 2, 3, 4 carbon chains only. These are the smaller items like methane. And this is why gases go to the top, right? If we think of these are the lighter substances, methane gas, ethane gas, propane gas, let's say for your barbecue. And then they get heavier or longer chained as we go down. Gasoline, kerosene, fuel oil, wax, asphalt. Think about waxes or asphalt, right? When they pour it on to pave, let's say the highway, this is thick, heavy stuff. When they put it down, it doesn't run right away off the road. It's very viscous. It's very sticky. This stuff is more or less solid, and they've heated it up to get it into liquid form. These are big chain hydrocarbons. So the key to this, we're going to use boiling points to separate out the crude oil into its parts. The smaller chain, the lighter molecules, the shorter number of carbon chains that they are, will go to the top, and they separate out, condensing back into their forms, and the bigger ones are at the bottom. Now, if we were in class, I would do a demonstration and show you a very simple form of distillation. I like to do it with orange soda. So I would take and open up a can of orange soda, and I would put it here in the Erlenmeyer flask, and I would turn on my temperature here to make it turn on rather high. I would go to about 150 degrees Celsius and heat this up. And what we would notice is in this orange soda, the water would actually evaporate. Now remember, there's lots of things in orange soda. There's coloring, there's aspartame, there's sucrose, there's glucose, right? There's lots of ingredients. But the water would evaporate and go through this tube first, and all filled with water droplets, right? It's condensing, so it's gas form. And when it gets over here and it hits a colder area, that's going to bring that gas back down, and I would be collecting pure water, H2O, out of the orange soda. And if I heated this long enough and collected long enough, I would fill up this test tube with distilled water, and all the extra stuff in orange soda, all the ingredients that aren't water, would stay back here. I have separated out by heat water from the other ingredients. Well, along with these physical properties to separate crude oil, there are some limitations. Those large carbon molecules are harder to separate out. And so along with fractional distillation, when we're heating them up and we're breaking them down based on lighter to heavier, down here where we have larger carbon atoms like the C25s and the C40s, the really big guys, we need to use another process. And that other process is something we're going to call cracking or reforming.
In this video, you will learn about the process of cracking, how it is carried out, and why it is done. From our video on fractional distillation, you should know that crude oil is a mixture of hydrocarbons with different carbon chain lengths. Smaller hydrocarbons have a lower boiling point and are more volatile, making them easy to ignite and more useful as fuels. Larger hydrocarbons have a higher boiling point, are harder to ignite, therefore not as useful as fuels. We use a lot of fuels in our day-to-day lives, driving cars, aeroplanes, lorries, and even heating our homes. This means there is a very high demand for small chain hydrocarbons. However, after fractional distillation, we find that we have a large supply of long chain molecules. The process of cracking breaks down long chain alkanes into a smaller alkane and alkene molecule. This allows the supply of short-chain hydrocarbons to meet the demand for them, as the longer-chain alkanes are broken down into shorter alkanes and an alkene. The alkenes are also useful as these can be used in the manufacture of plastics. Here is an equation showing that C12H26 is broken down into octane and butene. There isn't a set way that these molecules are broken down. In fact, C12H26 could also be broken down into decane and ethene, or even butene, pentane, and propene, as these equations show. The large hydrocarbon is broken down in quite a random way. Just note that in each equation, of course, since we had 12 carbon atoms and 26 hydrogens going into the reaction, the same must come out. The process of cracking is carried out in one of two ways, either by thermal cracking using high temperature and pressure, or by catalytic cracking at low temperatures and pressures but using a catalyst. In thermal cracking, the large hydrocarbons are heated to temperatures up to 750 degrees C and a high pressure of 70 atmospheres. This high temperature and pressure breaks the bonds between carbon atoms to make smaller molecules. Catalytic cracking is the method used mostly in industry today. The large hydrocarbons are heated to around 500 degrees C and are passed over a zeolite catalyst. The catalysts chosen tend to break the bonds in the large hydrocarbons and make molecules of between 5 to 10 carbons in chain lengths, making them very useful in petrol. Now, at the end of this video tutorial, you should know that cracking is the process in which large alkanes are turned into smaller alkanes and an alkene molecule, and that there are two types of cracking: thermal cracking using high temperature and pressure, and catalytic cracking, which is the method preferred in industry as it uses lower temperature and pressure and produces more molecules that are useful in petrol.
So we've already looked at physical properties or physical properties. We are going to now look at chemical. So catalytic cracking is when we take a large molecule and we break it into smaller molecules. I always like to think of this as an egg cracking. We start with a big egg and it breaks into smaller pieces. And again, when you crack an egg, it can break into different size pieces or different amount of pieces every time. So we're going to start with a large alkane. When we crack it, it'll break into, for sure, an alkane and an alkene. Now, I chose decane. Decane, C10, can break into octane, C8, and ethene, C2. Remember, it's always an alkane and an alkene, so ane. So twice as many plus 2, and then just twice as many. Again, like the video said, decane doesn't have to always break into octane and octene. This time I have decane breaking into hexane and butene. So it's one of those where, and again, the video, it can break into 3 pieces as long as whatever we start with, 10 carbons, 22 hydrogens, is what we end with. 10 carbons, 22 hydrogens. Why are there so many possible products when cracking? It's because the chains are so long that there are many different combinations. 2, 3, possibly 4 if we have a long enough chain of combinations of products that could be formed. Now, ethane cracking, also called dehydrogenation, is the case of when 2 hydrogen atoms are removed from an ethane molecule. So here we have a saturated ethane molecule, right? 2 carbons, 6 hydrogens. If we remove, let's say, this hydrogen and we remove this hydrogen, so these guys go away, this carbon has only made 3 bonds. This carbon has only made 3 bonds. So it's kind of like these 2 hydrogens, when they went away, their little drawbridge is going to go down, and we're going to form a double bond here. So we have turned ethane cracking into ethene. It also releases hydrogen because remember, whatever you have on the left, you have to have the same total on the right. And so this is our way of making ethene. We're converting an alkane to an alkene. Now, the question is, well, why is it so important to make an ethene? And that's because ethene is so hugely important for what we can make out of it. This includes plastics and paints and dyes and antifreeze and adhesives and carpets and pesticides and fertilizers and all these pharmaceuticals. Ethene can be turned into so many things. It's so important that we know how to crack ethane, a smaller molecule. Hope this clears it up.